Leetcode 208, implement trie or a prefix tree. And as you can see, it is a medium type problem. At least that's the classification from their side. But here on the right side, let's take a quick look. We will have to implement, as it's already stated in the title, this whole class. They have designed the public interface, but we will have to figure out on our own the internals and, of course, what exactly are those functions supposed to do, which also takes time. So maybe conceptually it's a medium type problem, but definitely when it comes to the sheer amount of writing, and of course we'll try to use certain tricks from Python, which will significantly shrink the possible code, but still the sheer amount of writing is quite significant. And I would say that in that sense, it would be hard problem, but maybe conceptually it's not really that difficult. That's why they are classifying it as medium. And here is the description. A trie, pronounced as trie, or prefix trees is a tree data structure used to efficiently store and retrieve keys in a data set of strings. So we can have multiple ways in which we store groups of strings. But because certain strings are more common than others, we can store them in more efficient manner if we store groups of strings. So not just one, but trie allows us to store multiple strings together. And if those strings share a lot of commonality, meaning that certain parts of those strings are repeated, then we can take full advantage of a trie and save a lot of space. And also while searching for those keys inside the tree, we can also do it in an efficient manner. And there are various applications of this data structure, such as autocomplete and spell checker. So tries are used in many different settings, but one of the most common ones are autocomplete feature, which is a very common thing, and spell checker, which is also a very common thing. And we have to implement the trie class. As we can see here, it's already prepared for us, where we will have a constructor. So whenever we call the object, we will create an object, we initialize it, and those three methods: insert, which allows us to add or insert the string into the trie, and search returns true if string word is in the trie, it was inserted before, and false otherwise. So we can search for prefixes and we can search for complete words, and that's the whole magic behind this trie, is that we will be splitting it into sub parts and we'll be going one by one. And this search, which is actually contains, maybe that would be a better word for that, has to return a Boolean value, meaning that if exactly the whole string like this was inserted before, then we return true, false otherwise. So if someone enters a sub part, even though it's inside the tree, this should still return false. And the second Boolean method is starts with, which exactly deals with the thing that I was just describing before, meaning that it returns true if there is a previously inserted string word that has the prefix, and false otherwise. So if there is like a part of the word that was inserted and which they are looking for here is provided as an argument, then we still return true. So in this case, in the case of search, we have to have the full one. In the case of starts with, we can have partial or the prefix, which is a more correct term. And here's an example which doesn't tell us much, but basically those strings here are supposed to represent the calls to different methods from our class. And the second list are the arguments that they are providing. So first of all, they will create, and here is like an explanation of what this is supposed to mean. So first they will create the object, then they will try to insert apple, then they will search for apple, and the whole apple was this whole word was exactly like this inserted before, meaning that here we return true. But if you search for app, which is a prefix of apple, then we return false. But if we use it with starts with method, then we have to return true. Then we insert app, which is has some shared parts with Apple, yeah, and that's something that our internal implementation should handle to store it in an efficient manner. And now if we call search on app, it was already inserted like this before we return true. Okay, so let's copy this and let's think about how we can possibly implement it in Python. And let's also copy the public interface. This we don't need, like this, the function like this, and like this. Yeah. Now we have to figure out what will happen behind the scenes. Okay. So generally, when it comes to trees, tries included, and any tree-like data structure, so graphs as well, and there's usually, not always, but you can use it as a rule of thumb, a way to implement them in an easy way using dictionaries. Now, under the hood, use dictionaries. And I made spelling error like this. Yeah, and in Python, of course, we have multiple dictionaries or dictionary-based structures. The most common, of course, is dict, but there's also default dict, which we will use this time, which has certain advantages over raw dict, mainly that whenever we access it, yeah, using providing a key, it never throws an error. Yeah, so if there was nothing there, we can specify like a default value for it, which makes it a little bit easier to work for it. And this default value usually is 0 or like an empty dictionary if it's like nested dictionary like we will do here. And that's the main idea behind this. So if you haven't worked with dictionaries before, then definitely give it a try. Well, I suppose that you have worked with dictionaries, but default dict might be something of interest. And that's something that might be useful to use in this particular case. And we will have, by the very beginning, an empty set. Let me make it small, since I'm always clicking on those objects. Yeah. So at the very start, we will have an empty set. Even make a mathematical symbol for it, like this. We'll have an empty root, and then as we add words, as we insert them, we'll be splitting into characters, and each character will be stored in a separate node. So let's say that's our initial tree representation, and we want to add following words: car, cat, dog, and do, and like this. Then each of them will be split into individual characters. Those are the parts. Of course, you can have different tries which tokenize words in some different way, but in our case, we'll be just splitting them into individual characters. And the first word that we are adding is car. Why is it so small? Let's make it bigger. Like this. Yeah, and of course the first character is C. Yeah, So that will be the first word stored in the first node of our tree. Of course, trees consist of nodes. Yeah, and then the next is A. And then the next is R. Like this. And we have to have a way of marking the last element. And so here we'll mark it with a green box, but in the code we will think about some other way of marking it. Yeah? And here comes the magic. We add now the next word, cut. Yeah, C is already there. We don't do anything. A is already there. We don't do anything. We only do something for T. Yeah, that's it. And now we add dog. That will be the second. Yeah, we have to start again from the root because we don't have any node which connected to the root which has D inside. Yeah, so we have to create a new node again for D. Yeah, and then O, and then G. Yeah, that's the way it works. And now if we want to add do, we don't have to do anything except for marking O as also possible or valid termination character. Yeah, so in order to implement this idea in the code, we will create a new class. Well, here are the steps. Create a new class called node. Nodes will store recursive, or maybe not recursive, nested is a better word, more appropriate here. Relations to children and further ancestors. Each node will represent a single character, and this character will be key in the dictionary, and we will mark a special marking for termination character. Like this, that's the plan. And this will be our backend, or what will happen behind the scenes. And we will operate on those nodes in all three public methods. But we can start already implementing, and then we will go back and think about those three. So 3 methods. And a class called node, which will store a character, and we will not provide it like this. We will provide it through public interface for the children, which will be a default dict of what type of node. And so the children will be nested and as many levels as it's necessary, and each next value in this dictionary will be a node as well. Yeah, so an empty, like basically when you access the key which doesn't exist yet in the dictionary, the default dict will create a new node object for you. And we will have also this marker for determination called end. Yeah, and it can be a boolean. So by default is false, but we can also make it true whenever we want, because both of them are public. and that's the inner data structure which will operate on inside the trie. And already we can also create a root, which will be the first node. I think that would be it when it comes to the node. And thinking if we need anything else, we might now think about insert. Yeah, so how can we add new elements to it? So let me move it here. And what we will do inside is first pull the root, then iterate through each character and update slash leave the way it is. Yeah, and because we use default dict, this will be very easy without any if else. The appropriate node. Yeah, so we'll have to go from the root and then new node, so on, by keeping those connections, and the connections will be kept through the children property. Appropriate like this. It is appropriate and to each character, and by the end the last thing is mark the last node as terminal, and that's it. So basically 4 steps of insertion. So the first node that we will use here is our root. And then we'll go for character inside the word. We'll go through each character, and we'll be pulling new nodes by going from the first one that we initially pulled, which is the root, and then setting the character as a key inside the default dict in children. Yeah, so if it didn't exist yet, the default dict will create a new node, but if it existed, it will not do anything. It will just return appropriate node. And by the end, we have to mark it as how did I call it? End. And that's it. That's the whole philosophy behind insertion. Now search and start with. For that, we will create a new method, which will be private, called walk. And let's think about how to walk through that structure in order to distinguish between those two cases. So in search, we will want to reach the node which has end set to true, and it starts with it's enough for us that we'll have each element of the prefix inside, but doesn't have to be, the last one doesn't have to have end set to true. So let's copy both of them here, and let's ask how to traverse that tree. And of course, the answer is starting from the root. But what else? Let's move this here to the side. And we'll do the same thing as here in the second part, iterate through each character, and maybe to make it more precise of the word. Yeah, so here I meant the input word, and here update leave the way it is appropriate the node. Yeah, so pull the root as the first node, and that will also be the first element here through each character of the word. And here we were and update if the weight is appropriate, and I will not modify it, but basically here we are I was talking about the node, not about the word. Yeah, so we have those two things. One is the node and one is the word. And here, how do we traverse? Yeah, in both cases we will need to traverse it. We'll pull the root first and iterate through each character of the word. And we have here we were adding stuff to the children, and here we are getting or retrieving. So check if the character is exists, or maybe like this, exists already in the children. And two options. If no, return 0. Not 0, but none. And if yes, continue. If yes, continue. And go here, and so on and so forth, up until either we get none or we get to the end and return the last node. Return the last node. So both of this will, under the hood, operate on this logic. And for that, we will create this walk method, which will get a word and will return optional object of, not try, but optional node. So the first one, of course, this part we can copy. And we first get the root, then we go through each character in the word, and the next node will be the node, but not accessed like this, since this is creating it because it's the default dict if it doesn't exist. And we want to check if it exists. That's why we'll have to use get instead of the square brackets. And if node is none, return none. Otherwise, continue. And if we reached the end, we have iterated through each character and found a node appropriate for this, then we return the last node. And that's it. And this, for search, we basically call it self walk on the word. And we return node is not none, and also node is the terminal node. Yeah, so and is set to true. For starts with, it's enough if the node is not none. So that's it. That's the whole try. Now let's see if it works and if we pass all the tests, or do we need to add any modifications. And word is not defined. Here it's called prefix. And the first test case is accepted. So now let's see on all the test cases. And we beat just 30%. Let's try to rerun. I have to wait a little bit since I'm not a premium member. And now we beat 70%. And that's because there are just 16 test cases and it's completely random. And so I think that before I even got up to 90%, so basically this implementation is quite optimal already. Of course, there are even better, more optimal implementations, but this is something that is, I think, very easy to use and easy to remember. and takes advantage of the Python features like default dict, which is also a good thing whenever you are programming in a given language to take full advantage of this of its features.